Hydrogen and chlorine are two nonmetals. When they bond together, form a covalent bond, a polar covalent bond, and hydrogen chloride actually forms a polar molecule. And just as we learned that ionic compounds can be dissociated by water, so can some molecular compounds. And this polar hydrogen chloride molecule is an example of that. Water is able to pull the hydrogen and the chloride ions apart and form a shell around them and keep them as solvated ions in solution. Any substance that increases the hydrogen ion concentration of a solution is known as an acid. If you recall, pH is calculated by taking the negative log of the hydrogen ion concentration. So the more hydrogen ions you have in solution, the lower the pH is going to be, and the more acidic the solution is going to be. So a strong acid, then, recall the definition of a strong acid is one that completely ionizes. If we have a strong acid and a weak acid of similar molarities, the strong acid going to completely dissociate is going to give us far more hydrogen ions than the weak acid of the same molarity would. So a strong acid is going to have a much lower pH than the weak acid would. This is sulfuric acid, and sulfuric acid is also a strong acid. Here we have the sulfur as the central atom, and oxygen, 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 oxygen. And here are our ionizable hydrogens. So the formula for sulfuric acid then, H2SO4, we've got two hydrogens in there, and so this is a diprotic acid, or two ionizable protons or hydrogen ions. Sulfuric acid, though, will easily ionize one hydrogen. The first hydrogen that is ionized from the molecule, then, if we take a proton off of here, what we're left with is going to be then HSO4 negative. And so, since we've lost a proton and we now have a species that has a negative charge attached to it, trying to remove that second proton is going to prove to be a little bit more difficult. Remember, we have an overall negative charge on here, and so to remove another proton is going to take quite a bit more energy. So the first hydrogen will ionize very readily from sulfuric acid. The second hydrogen ion will not. Then we'll compare that to acetic acid, which is a weak acid. And the formula for acetic acid can be written a couple of different ways. It could be HC2H3O2, or it can be written as CH3COOH, which is the way it looks. We have a carbon here, CH3 hydrogens, and then another COOH. And this hydrogen right here would be the ionizable proton for acetic acid. Now, it's a weak acid, meaning it doesn't completely ionize. So some of these hydrogens are going to come off of here and leave us with hydrogen ions, and then we have what's left over are going to be the acetate ions. And as we said before, this only happens to a certain extent before the system reaches an equilibrium, at which point we would actually have all three of these species present. And why don't all of these hydrogens ionize very easily off of acetic acid? Well, look what it's bonded to. It's bonded to oxygen, and oxygen's one of those three really electronegative elements, fluorine being the first, oxygen being the second. So this oxygen actually has a pretty good grip on that hydrogen due to its greediness for the electrons, and it's not going to readily give that hydrogen up. And that's what makes acetic acid a weak acid. bases, by definition, are proton acceptors. A base is a substance that's going to produce hydroxide ions in solution. So our strong bases, one of our most famous strong bases, is sodium hydroxide, also known as lye or drain cleaner. In water is going to, since it's a strong base, is going to completely dissociate and form sodium ions and hydroxide ions. Weak bases work a little bit differently. Ammonia is an example of a weak base. Remember, if you drew the Lewis structure of ammonia, you would have an unshared pair of electrons up here on that molecule. And ammonia, when it reacts with water, will actually, to some degree, be able to attract one of the hydrogens off of the water molecule, which will come and attach itself right there to that lone pair of electrons. And so if we take this proton or hydrogen ion off of water, what we're left with is going to be a hydroxide ion. So what we have is ammonia, NH3, plus water, H2O, is going to form, after that proton is removed from the water and attaches itself to the ammonia, we end up with NH4 plus, or ammonium. And, of course, what's left from the water are hydroxide ions. So ammonia is a weak base in that it acts as a proton acceptor, forming hydroxide ions by removing the hydrogen from the water molecule. The result of an acid-base reaction is neutralization, or the formation of a salt and water. And by definition, a salt is an ionic compound that's the product of a neutralization reaction. So an example of this would be if we took hydrochloric acid, and we'll take sodium hydroxide, a strong acid, and a strong base, and in an exchange or metathesis reaction, we would have the sodium and the chlorine forming sodium chloride, and then the hydrogen and the hydroxide forming water. Now, if we wrote that as an ionic equation, or a complete ionic equation, since the acid is a strong acid and it's going to completely ionize in water, we would show it as ions in our equation. So we would have hydrogen ions and chloride ions as a result of the ionization of the HCl, and sodium hydroxide, being a strong base, is also going to fully dissociate, giving us sodium ions and hydroxide ions. And then on the product side, sodium chloride we know to be a soluble salt, so we would identify that or show that in its ionic form also as sodium ions and chloride ions. And the final product here is going to be water, and H2O, being a molecular compound and not an ionic compound, would be left in its true form as a liquid. And so, if we were to abbreviate this to eliminate our spectator ions and write the net ionic equation, let's find our spectator ions. Here we have chloride ions on both sides of the equation in the same form. Here we have sodium ions on both sides of the equation in the same form. Here we have hydrogen ions on the reactant side going into the production of water on the product side. So the hydrogen and the hydroxide are actually what are producing the water on the product side. So our net ionic equation for this reaction would be H plus OH negative forms H2O. And that's the net ionic equation for the reaction between a strong acid and a strong base. There are other bases besides hydroxide that will react with hydrogen ions to form compounds. For example, the sulfide ion. An example of this would be hydrochloric acid and sodium sulfide. And we would have 4 products: sodium chloride and hydrogen sulfide gas. And this gas smells like rotten eggs, so it's pretty nasty. Now the carbonate ion, CO3 negative 2, and the bicarbonate ion, HCO3 negative, also both act as bases to form carbon dioxide gas. So if we took HCl, which you know hydrochloric acid's in your stomach, and added to that sodium hydrogen carbonate, which is baking soda, which was an acid back in the old days, what we would have for our products would be, again, sodium chloride. And when we put the H and the bicarbonate together, we would have H2CO3, or carbonic acid. Now, carbonic acid is pretty unstable. And so what happens to the carbonic acid then is it actually breaks down into carbon dioxide and water. This is another one of those systems that forms in equilibrium. We'll talk more about that in a later chapter.